sense, you could say that it's jargon, but on the other hand, the physical effects associated to this kind of situation are real effects, are of interest for physics, not only from a fundamental point of view, but also from an experimental point of view. This is the very crucial point. Let me just mention, I mention it again, this paper, which is in collaboration with Marco Baldovin, Stefano Iubini, who is sitting there in the audience, and Angelo Vulpiani, where we tried to provide a much wider and complete overview and understanding of this kind of problem, okay? What I'm going to tell you today is not a summary of that, it's just a spot on some points which, in my opinion, are the crucial facts. Now, let me go to the generalities of the problem. So once you have to deal with a Hamiltonian model of this form, which is what you can call a separable Hamiltonian, where the kinetic part is just a quadratic form in the momenta, while here you have a potential which depends just on the conservative potential, which depends just on the coordinates or positions of particles. I is just an index that enumerate the sites, for instance, on a lattice. This Hamiltonian describes a set of a system in one dimension. It could easily generalize to higher dimensions. That doesn't make any problem. Well, you can compute for this kind of models the entropy in some way. All the problem is absolutely well defined. And what you find is that if you define the entropy as the derivative, the inverse of the partial derivative of the entropy with respect to the energy is the value that you attribute to this functional h, Hamiltonian functional, then you will always find that this temperature is definitely positive. No way. Okay, so this is the basic of statistical mechanics. That's why when you introduce a statistical mechanics measure, like the Gibbs measure, you can write e to the minus beta h and interpret beta as the inverse temperature, positive, absolute temperature of a system. So no problem here. But there are situations where this is not true. There are other kinds of models in physical interest that do not belong to this wide class of Hamiltonian models. And one example, probably at least to my knowledge, the oldest one, goes back to Onsager in 1949, when he introduced a Hamiltonian which describes n vortices of vorticity ki. Ki may be positive or negative, meaning that you can have a vortex which is clockwise or counterclockwise, and coordinates x, y, and yi in a two-dimensional inviscid fluid, which is described by this Hamiltonian. And you see that the interaction is ruled by the sign of these values of the vorticities times the logarithm of the distance between the center of the vortices. And the phase space of this model was proved, I'm not going to the details, it's a very famous example, proved to be bound. Okay, so the energy in such a way that if you take an energy larger than a certain maximum value of this energy that you can compute, you find that the temperature results to be negative. The absolute temperature results to be negative. I mean, okay, say, okay, the absolute temperature defined, then I come back to the harsh dispute which came in the recent years about the proper definition of entropy, if it is associated to the surface or to the volume entropy. Okay, but let's forget it for the moment. At this level I say this temperature means that it's going to be negative, is because there is a phase in this model where when the energies are larger than this maximum value, where you observe a very strange phenomenon. The system behaves in a completely opposite way. If you add energy, this energy is not shared all over the system, but is clustered in some specific region, which is completely contrary to what your standard experience with the previous kind of Hamiltonians. This is a very well-known example. So, I mean, and you see, the argument of this oldest example goes more or less as follows. If the system is bounded to a closed domain, that's a very important fact, with the Lebesgue measure, which is defined here by mu of A, one can prove this inequality, meaning that the integral between, for values of energy between minus infinities and any value of E, of the density of states omega of E is the density of states, which is a well-defined problem. You have a Hamiltonian, then you just measure the density of states. Forget about definitions of entropies, okay? Well, you find that this, if you can prove this inequality, and you can prove for the model that was at hand before, proposed by Onzager of these vortices, then you find that because of the fact that omega of E is positive, the first inequality implies that it cannot be a non-decreasing function of energy. Otherwise, this integral wouldn't exist. Okay? So if it cannot be a non-decreasing function of energy, it must be, in some sense, a decreasing one, and that means that what you define temperature, absolute temperature, should be negative. Are we really concerned with that? I think it's more a semantic problem. The problem is that what happens in this system if the energy is larger than its maximum energy? Well, by the way, if you define the microcanonical entropy, so in some sense I'm contradicting myself, but let me go to more, frequent or typical definitions. And you take for the definition of the entropy KB Boltzmann constant times the logarithm of omega, you can conclude by the previous argument that the inverse temperature actually is negative. But as I said, what does it happen? It happens that if you go to this larger energy, the vortices that are around, suppose you adiabatically change your temperature, which in some sense are more or less spread all over this two-dimensional checkboard, start to condensate. The sort of clustering effect, which takes together larger and larger vortices. So there is an energy cascade from smaller scales to higher scales to form more and more coherent structures. By the way, this is what was conjectured by Onzager in 1949. What is relevant for a physicist is not only that you can prove things about the Hamiltonian, but you can make an experiment and see it. And this is actually what they have seen in a numerical experiment by these people here in 2015. So you find that negative and positive vortices separate into two large clusters for energy larger than its maximum energy. So there's a segregation effect. You find that there is a large energetic cost to reach this configuration. So you have to pump energy in the system in order to reach this kind of situation, although at some moment you stop. So it's enough that you are at a higher energy than the maximum one to observe, to a sufficiently high value of the energy to observe this effect. And then the mechanism is that there is, as I was saying before, these small scale structures that transfer energy to the higher scale structures. What is even more important is that in 2019, these people here actually observed this effect in a superfluid of Bose-Einstein condensates. So it means this is physics. You see a very peculiar phenomenon, which depends on the fact that the kind of interaction you're dealing with is such that the Hamiltonian is bounded. Okay? That's the main message. Then if the entropy, which is defined that way, includes the fact that if you make the derivative with respect to the energy and you find that the inverse is negative, okay, it means that there is a negative temperature, but I don't care about that. I care about that you observe this effect, okay? Well, the most known and classical example is the one, experiment performed in 51 by Purcell and Pound on this kind of nuclear spin in lithium fluoride crystals. And then you find that also in this case, you can define a spin temperature due to the fast relaxation to equilibrium of spin interactions, while the interaction of the spins with the background are essentially negligible. And then you have an equilibration of this system on a strong external magnetic field. And then the adiabatic reversal of the spin magnetization in a high energy state lasting over 10 to the 2 seconds. So orders of magnitude larger than the time that you observe the relaxation to this equilibrium state. In this sense, you define an experiment what you would attribute the significance, the meaning of an equilibrium state in statistical mechanics. This is a very classical example. Ramsey in 56 provided an interpretation of this further experiment. By the way, this kind of model is still a situation where you have a bounded energy because the spin chains have a bounded energy. They cannot go overtake to a certain value. And so he established the general conditions for negative temperature states in a general statistical mechanics frame. These are the conclusion of Ramsey. The elements of the considered system must be in thermal equilibrium. So a thermal equilibrium, according to Ramsey, is compatible with absolute negative temperatures. The possible energy for lower level states of the system must be bounded, which is the case of the lithium fluoride spins. And the system must be thermally isolated from all systems that do not satisfy the previous conditions. What does it mean? It means that you put this system in contact with the heat reservoir at positive temperature, it will destroy everything. So in some sense, this has to ring a bell in your head. It's important that the system is not in contact with the standard heat reservoir. So the general situation that you would expect typically to observe such a behavior, such a strange behavior or a peculiar or anomalous, as you want, behavior associated to absolute negative temperature, is that the system should be isolated or at most in contact with another system with the same negative temperature. Has this some implications? Well, I put on your head a suspicion. It's clear that if you would like to assume that you have ensemble inequivalence, or if you want that you state that the canonical measure is the same than a microcanonical measure, with absolute negative temperatures, you will probably go into troubles. These two things are not compatible, probably. Actually, and then I can say they are not, but this is the conclusion of my talk. Now, okay, let me skip this. I don't have no time to discuss long this thing. Then what happened? Recently, there was a harsh debate about this question of negative temperatures. Many people raised arguments against the idea that negative temperatures should be really associated to equilibrium states and more generally should be compatible with the basic rules and relations and theorems of standard statistical mechanics. So they cannot be really considered as genuine, oh God, the new generation, as a genuine equilibrium states. Now, the problem is that all the debate pointed on a dispute about the very definition of entropy. As I was saying at the beginning, this doesn't concern me too much, but on the other hand, that was the level of the debate, and then I have to report it. How to define entropy? There are two definitions. What is called in jargon of statistical mechanics is volume entropy and what is called surface entropy. What does it mean? You can define entropy considering the whole number of states inside the volume of a space, the overall volume, or on the upper surface of constant energy. Everybody knows from the time we was in university studying these things that these two definitions essentially coincide if you make the thermodynamic limit and the system is a standard one, like the one that I was mentioning at the beginning, a separable Hamiltonian or anything else. But this is not the case for this kind of systems. These two definitions are not only for this system, but in general, really equivalent. And all the dispute moved not from discussing if these physical effects that you observe in the system are really relevant or of some interest, but about a sort of religious the debate between the existence of, I don't know, the virginity of, sorry, or not. I mean, I don't see really the point, but on the other hand, this strongly pushed Stefano Ubini, Marco Baldovin, Angelo Vulpiano, and myself to write down that physics reports, which I reported here again. And then we can state, believe me, then you can go and read and probably, hopefully, criticize if you were wrong. But we studied all the probability in all directions, including definitions concerning generalization to negative temperatures of Langevin equations, Fokker-Planck, intuitive relations like Gibbs 1 and so on and so forth, local equilibrium, blah, blah, blah. Then nothing says that you cannot attribute negative absolute temperature a meaning which is not compatible with standard thermodynamics. So negative absolute temperatures are genuine thermodynamic states. Nothing contradicts their existence. Nothing basic, nothing fundamental in statistical mechanics, okay? But on the other hand, I insist, the point is, are these effects relevant to our knowledge about what happens in some models of physical interest? I want to point out that this dispute appears much less relevant if you take into account that what really matters once you define the Hamiltonian is this functional, which is the natural one, the density of states. Forget if the logarithm has something to do with the entropy, who cares? Look at this quantity, which is very well defined, and then you want to understand if there is a way to consider from this quantity a criterion that may guide you to understand if the system may admit or not negative absolute temperatures. I want to point out that many people, not the expert in the field, but many ignore that Machlup, which was one of the collaborators of von Zager since many years, provided a very interesting, more general criterion than the Ramses one, and the criterion is this one. He claimed that not only bounded energy systems, but also systems such that the expectation value of the Hamiltonian at infinite temperature, beta equals 0 means that, okay, which is by definition this expression here, computed at beta equals 0, so this one. If this is strictly bounded by infinity, this system may admit negative absolute temperatures. The case that we discussed before about bounded system is a special case of that. But this is the most general criterion I found in the literature, and you can prove it. Actually, it is very effective. Let me give you an example of a model. Then you will learn about it later in other seminars, so I hope to say just a few words, which belongs exactly to this class of models, and which is not bounded, but which admits negative absolute temperatures. This is the discrete nonlinear Schrödinger equation. It's not the only example, but it is a very well-known example. Okay. You immediately realize that since this variable z is a complex variable, which can be written as qi plus I pi over square root of 2, which means that simply that it is a sort of quantum-like variable. And here you observe that you have here a quartic nonlinearity. And the important thing, which is really crucial for the physics of the problem, which is strictly related to the existence of negative absolute temperatures, is that not only the energy, but another quantity, which is what is called the total mass, okay? You can understand it because it's just the sum of the amplitudes of the z, which can consider a sort of amplitude of a wave function in a loose sense. This quantity is conserved. So in this system, you have conservation of mass and energy. And then you have a situation which obeys the criterion by Machlup. If you make the calculation, you discover that this is the case. Actually, this is summarized in a diagram that you will probably see again later, where you can find here the density of energy. So this is the E over N. This is the density of mass, so it's big A over N. N is the number of particles. The chain is a one-dimensional chain. And then you see here, you have a situation here where you have this blue line that tells you that you cannot find states below these blue lines because they're not compatible with any kind of initial condition, okay? And it's clear if the A and energy are conserved quantities, this is exactly the ground state of your system. There is a word region here that I named RP, which corresponds to the region of positive temperatures. Here is the line, this dashed red line, which corresponds exactly to the Machlup criterion. The value of A and energy where the temperature is infinite. Is infinite all over this dashed line. You make easy calculation, you find it easily. But then there are states here that do exist. I mean, you choose this value of density of energy and this value of density of mass, and then you wonder, what does it happen here? Well, there you have negative absolute temperature states all over this region. This was found for the first time by Rasmussen and other people in 2000. And I mean, there is the original paper is a very, very nice one, very interesting one, but it's clear that how to handle this problem of negative temperatures is not at all obvious. The authors try to establish a connection between a Gibson and a microcanonical measure, and that was really, in my opinion, making their point diverge to the wrong direction. So that's not the good way to interpret what happens here. Actually, what happens here, let me say words, is that while here you can claim that a canonical and a macrocanonical description are totally equivalent, this is no more true in this region. The only significant measure is the microcanonical one. If you pretend to apply a canonical measure with a negative temperature, nothing happens. You cannot make it. What happens in these negative temperature regions? I spent just a few words. I hope that Paolo and Antonio maybe later will discuss about that. No, but in this phase, what you observe, you start from an initial condition. I mean, you are somewhere here, for instance, here. You start from an initial condition, but you put energy everywhere more or less in a sort of uniform way, and then you make the system evolve. And what you observe there are millions of units in natural time of evolution. You observe clusterization of energy. These lines, these rows, which is dark rows, means that you are forming breathers. Breathers are the typical solutions of the system. So in some sense, the system in this area, at variance with the region where you are here, when you are here, but if you put energy, it is spread all over the chain. In this region here, the energy concentrates in specific regions. These excitations live for an exceedingly large time. They die, but then at some moment they come again, forever. And over any reasonable expected time that you can compute, they last there, they are there, they never disappear. And I think that those who are going to speak after me will explain to you much more details about this very interesting effect. Now, summary of the results and the interpretation. I think that my time is almost over. For this model, well, the microcanonical partition function can be completely explicitly computed close to beta equals 0. This can be done. Don't ask me how, but I mean, it's a technical problem. Then you can use mathematics. Fortunately, we have still scientists, at least of my generation, are still used to use mathematics and make a calculation. Today with data, we solve everything, but okay, I don't believe that. Anyway, then you find that in this calculation, you discover, immediately that, that this region here corresponds to a first order phase transition from this phase, positive temperature phase, to the -1, negative absolute temperatures, where typical structures are localized in space. And then you have a breaking of ergodicity and inequivalence of ensemble, as I was saying before, in these negative temperature regions. There is no way to map a microcanonical measure into a canonical one, while it is possible to make it below that dashed red line. And then negative temperature equilibrium states do exist, actually. You observe them. They are there, like the vortices, the condensate in the case of Gonzaga. I want to show you one final picture that may convince you that this is the physical effects are really sizable and interesting. Because you may wonder, okay, you have bothered us about all these questions related to the equilibrium and so on and so forth, but what does it happen in out of equilibrium? Are out of equilibrium states compatible with negative temperatures? I'm almost done. Well, look here. Here you have a chain, the DNLSE chain, which is thermalized at its boundaries with positive temperature. Here is the inverse temperature beta. Here you have positive temperature. Here you have a positive temperature. And here you have different system size of this chain, okay? And what does it happen? The system produces naturally a region which is at negative temperature. So if you drive your system out of equilibrium, the system very naturally produces a state, an intermediate state, which is at negative temperature. Why? Well, obviously, if you go back to this picture, it means that you have put something here, some initial condition here, and the typical way in this phase diagram, these 2 points in the positive temperature part connect to each other is through a line crossing the infinite temperature dashed line. And this is done by itself. Nobody imposed to the system to make that. Okay? I think if one has doubts about the meaning of these negative temperature states, despite here use inverse temperature as an indication in this diagram, I think that nobody can object that it is a perfectly genuine and sensible representation of what is going on. Obviously, you can drive the system out of the situation, changing the values of the temperature at the boundaries. Look here, for instance, if n is 511 sites, all this line is positive. But as soon as you increase the system, since you give more space to fluctuations to condensate somewhere, a sufficiently large amplitude, this amplitude, once it has been condensated, will never die. That's the point. So in some sense, the probability of condensating one of these structures depends clearly on the system size. But it's clear, statistical mechanics deals with n going to infinity, no problem, okay? Finite size effects are known to be sizable and important. But from a conceptual point of view, these negative temperature states do exist. Thank you.
Okay, thank you very much. Nice talk. Questions? Yeah.
Roberto, very interesting talk, really. And what I see in the last, if you can,
sure.
It seems that if you increase the number of degrees of freedom, if I read well, so you have that the system stay much more time in the negative part.
Well, no, this is what you observed after a very, very, very long time.
At very, very long.
It never go back. For instance, if you take this green line, it never go back. Stays there. The important point, by the way, is that if you can easily observe that since the coordinate here has been scaled to n over big N, this tells you that this effect is more and more sizable as soon as the more you increase the system. Why? Because you leave more space.
Okay. So in the limit of very large N,
everything will become.
Everything. Okay. Okay.
Everything. The boundaries.
Very nice talk, Roberto. I wish to ask one question concerning the interpretation of this result in terms of the property of the dynamical system that you studied, that is the discrete nonlinear Schrödinger equation, is well that you know that is a completely integrable infinite dynamical system. Okay, so this equation have envelope soliton, which is have soliton. Okay. Okay. No, the discrete, okay, but the continuous is integrable. So my question is, which is the interpretation of negative temperature concerning the property of the continuous solution?
Well, this is, at least to my knowledge, consider that this is a very difficult, technically non-trivial pathway to follow. First of all, we have to perform continuous in a proper way. this doesn't mean at all that the singularities or properties that we observe in the discretized system could survive if you made the right thing. Okay? By the way, the integrable model admits the existence of expectations, similar to the, but they are not attributed, nor it admits the existence of part zero mode, breakdown energy. So the way of handling this thing is not at all obvious. By the way, all the big efforts that are being done by the large part of the mathematical community in trying to understand, to extend generalized Gibson ensemble to integrable models certainly pertains the continuum version of the nonlinear Schrödinger equation. And I've seen something in the literature, but I must confess that I've not really understood up to the end which kind of implications could come from that. So my answer, unfortunately, is maybe sometime in the future, someone will understand it, or I'll understand it, and it's a very delicate point, in my opinion. For instance, there is another version of this model, which is integrable and discrete, which is the Ablovitz-Ladik problem, which is a modification of the nonlinear Schrödinger one, which has been longly studied by many people, like Mario Salerno and others. Well, in that case, you have a scenario which is very similar, but then in that case, it's very hard that they're going to invoke negative temperatures because the system has its own excitations, it has its own solutions, like in the total lattice. You don't expect that total lattice will have to deal anything with this kind of negative absolute temperature.